Professor.
Yep, I can hear you. Are you able to hear me?
Yes.
Okay, great. Let me start the live stream. All right. There we go. Hello, good morning, everybody. I hope you had a nice long weekend and you got to enjoy some of the sun. It sounds like we're going to get quite a bit of snow tonight, so that should be exciting. We'll see how that all shapes out. But we are just sort of continuing forward in our chapter 2 work. So just a couple of quick announcements. As a reminder, we do have our regular mini quiz on Sunday and homework, which is both based on the lecture that we'll do today. Next week, we'll be finishing up chapter 2, and our chapter 2 quiz will be a week from tomorrow. So next week on Friday will be our chapter 2 quiz. And just like the chapter 1 quiz, it's 10 questions, multiple choice. You'll need to find a 1-hour period to complete it during the day on Friday. And it will cover everything from chapter 2, which includes the first unit we did, which was limits and continuity. So I'll talk a little bit more about that next week, but just sort of wanted to put that on your radar as something that's coming up. So with that, there will be a chapter 2 review session on Monday and Thursday during the Zoom review session times, which is Monday 4 to 5 and Thursday 5 to 6. Those links are on Moodle, and I will send out a summary and a class announcement on Sunday with the links as well, just as a reminder. So that's what's coming up. Let me think. I don't think there's any other announcements. So why don't we go ahead and get started. So I'm going to switch over to the doc cam here. Okay. So the section we're talking about today is called Interpretations of the Derivative. And what that really means is the units of the derivative, like how do we talk about what the derivative is telling us, as well as one really important application of what the derivative can do now that we've started to learn more about the derivative, which we did in 2.1, also known as the instantaneous rate of change, as well as the derivative function, which is the video you watched last week. So as a reminder, we have 2 different sets of notation for the derivative because 2 different people developed calculus at the same time. So the Newtonian notation, which was done by Newton, is this prime symbol. So f prime of x, it could be f prime of t, but when you have this little notch up here, that indicates that we're finding the derivative. And when we do that, the independent variable is what is inside this function. So if we put a number in there like f prime of 2, that means that we are putting in 2 as the input that we are considering for the derivative. So remember that, because when we talk about units, the number that's going to be inside the function should have the same units as defined by the independent variable. Now, with Leibniz notation, we have dy dx. Okay, so the derivative of y with respect to x, this is assuming that we have y's and x's, but it's a little bit more clear, in my opinion, to understand where the units come from when we write the derivative like this, because it's going to be the units of the dependent variable over the units of the independent variable. Okay, and so sometimes you'll hear this called dy dx, like I said before. Sometimes people will say it difference in y values over the difference in x values. That's not as common, but the units do line up directly like this. Okay, so even if we're using the Newtonian notation, the units are the same because they mean the same thing. And so the units of the derivative are going to be the units of the dependent variable. So that's usually a y, doesn't have to be, but usually, divided by the units of the independent variable, which is commonly either x or t. So what we need to do when we start doing our work on this is figuring out what are the units of the dependent variable, what are the units of the independent variable, and then setting them up as a ratio in the context of the derivative. So we're going to be practicing this today in a lot of different ways, and just sort of looking at how we might think about this. So we're going to start with just one problem that we'll sort of walk through together, and then you'll get to practice on a bunch more. Okay, so we're going to start with this example here. Suppose that the position of a falling stone is given by S of t in meters and time t is given in seconds. Then f prime of 4 equals -7 means. So we're being asked to interpret the statement f prime of 4 equals -7. So we did this a bit back in chapter 1 with functional values, not derivative values. And it's sort of the same process where we need to figure out what are the units that go with 4, what are the units that go with -7, and how do we put them into a sentence that makes sense to relate them. So the way that we're going to approach this is that we have to remember whatever is being plugged into the function is an input, which means it's related to the independent variable. So what we want to do is we want to look at what units we have and figure out what is the independent and what is the dependent. So notice here, this is S of t in meters, and then we have time t in seconds. Okay, so S of t is going to be our dependent variable because S depends on t. So I'm just going to put dependent. Okay, so that meters is our dependent unit. And so here seconds are going to be our independent units. Okay, so now that we figured out those, now we need to look back at the problem, and we start with this 4. Okay, so 4 is the number being plugged into the function. And remember, 4 is the input, which goes into the independent variable. So the input is just the units of the independent variable. So when we talk about 4, we're talking about 4 seconds. Okay. Now, when we talk about the -7, this is where the derivative units come in, because the derivative equals -7. The rate of change at time equals 4 is -7. So this is where we have to bring in this definition about this ratio. So we have the dependent units over the independent units. So the dependent units are meters divided by the independent units, which is seconds. Okay, so how do we put this together? So we're talking about a stone that's falling. Okay, and so we want to bring the stone in and talk about the fact that it's falling. So we're going to say something like, after 4 seconds, or at time equals 4, the stone is falling at a rate of, and now here comes our number, -7 meters per second. Okay, so we know that the rate that it's falling is -7 meters per second, because that's the derivative units. But the 4 tells us when that rate occurs. So at 4 seconds or after 4 seconds, the stone is falling at this rate. Okay, so that's what we're going to be doing with a lot of our units. We're going to be trying to figure out what are the numbers attached to, how do we figure out those units. Just some sort of foreshadowing, actually, we'll come back to this. So let's jump down to an example. Okay, this one's a little bit tricky. Part A, I think will be fine. Part B is a little bit tricky, but let's take a look at it. So if S of t is the position of a moving object in feet, and time t is measured in seconds, find the units of the derivative of S of t, also known as the velocity. So you're not being asked about any particular numbers, you're just asked to find the units of the derivative. But then for part B, says if the velocity, v of t, of an object has the units found in part A, what are the units of acceleration, which is the derivative of velocity? So what that means is we're finding the units in part A, and then those are the units of velocity. Then we want to take that and take another derivative and see if we can figure out what the units of velocity are going to be based on part A. Now, this is a little bit tricky, but try it out. See if you can sort of figure out where we're going with this. Take a minute and a half, 2 minutes. Hopefully part A, you can get the units down okay. Part B, try to think about how we can bring the units from part A down to part B. Okay, so try that out, jot down your thoughts, and then we'll go through it together in about a minute and a half. Okay, take about 30 more seconds. All right. So here for example 1, we have this position function, which we're calling s of t, where this function s of t is in feet. Okay, so the dependent variable is going to be in feet, and the time t is going to be in seconds. Okay, since it's s of t, this is our independent value, and feet is our dependent value. And so when we talk about the units of the derivative, we would say s prime of t equals, and now we know from our definition before, we need the dependent units over the independent units, right? So that means our dependent units are feet, and our independent units are in seconds. So the derivative of position is going to have units of feet per second. So that's how quickly our function is changing. Now, another part of this that's important is that we're told that this derivative, s prime of t, is also known as the velocity, which means that the units of velocity are in feet per second. Okay, so the derivative of position is velocity. The derivative units are feet per second. So the units of velocity are in feet per second. Okay, so we need to carry that forward to approach part B. So part B says if the velocity, v of t, of an object has the units found in part A, so the units of velocity are in feet per second, so that is the dependent variable here, then what are the units of acceleration, which is the derivative of velocity? So what's changing from part A to part B is the dependent variable. In part A, the dependent variable is position. In part B, the dependent variable is velocity. What doesn't change, however, is the independent variable. So the independent variable is going to stay the same no matter how many derivatives you take. We are always measuring this in terms of time. So that means if we want to talk about the derivative of velocity, okay? We are going to take the dependent units, which are feet per second, okay, divided by the independent units, which is another set of seconds, okay? So the way units work are the same way fractions work. If you have feet per second, that's the same thing as feet per second squared. There's two of them on the bottom. So the derivative of velocity is going to have units of feet per second squared. And we are told in the setup here that when we take the derivative, that is known as acceleration. So acceleration is how quickly your rate of change is changing. And the units of acceleration are going to be feet per second squared. So I also want you to notice that since velocity was the derivative of position, that means if we take the derivative of velocity, we are going to get what's called the second derivative of position. So one of the things we'll do in the next class, we're not going to really do this today, is talk about what is the second derivative and what does it mean. And so we can kind of see some foreshadowing here that if we take the second derivative of position, we end up with acceleration, okay? But for now, we're really just thinking about units. So again, the original function was position. So that's something like 10 feet, 20 feet, 30 feet, whatever it may be. The first derivative of that is velocity, which is how quickly your position is changing. So we change by 10 feet per second, or 5 feet per second, or 9 feet per second, right? And then if we take the derivative of the velocity, we get something in feet per second squared, which is acceleration. So how quickly is your rate of change speeding up or slowing down? And that's going to be in feet per second squared. So there's these three things that we're talking about: position, velocity, acceleration, that are an important part of this conversation, because one of the ways that calculus is applied to a lot of things is through physics. So that's why we're having these sort of conversations. So let's go back to this example before, now that we've talked a little bit more in depth about position and velocity, okay? So before, when we did this interpretation, we were talking about a stone that was falling, okay? So think about this. If the change in position, so that's what that triangle is, represents a change in position during a time interval, delta t, so over some small period of time. Ooh, my phone is ringing. Sorry about that. And the object continues to move, this velocity we have is approximately that the change in position will be -7 times the amount of time we are changing. So when we talk about the fact that this is changing by -7 meters per second, we can approximate, right, our new position by multiplying the rate of change, -7, times the amount of time that we are going to be at this particular rate, okay? If the velocities are changing, then this is not very exact. And so in general, we say that the change in position is going to be equal to the rate of change times delta t for small t's. And so we're going to formalize this in a little bit in class today, but I want you to think about this as we go through some of the other examples, so that when we do get to the formal part of it, hopefully it starts to make sense on why that might be true. Okay, so let's look at the next example, where again, our goal here is to really think about the units of the derivative and what they mean. So here we have a graph, and it's of g of t. We want to estimate g prime of 20 using the tangent line, and we want to find the units of g prime of t. And so this particular graph is of the weight of a baby over time as it grows. And so we have the weight in kilograms versus the age in weeks. So I want you to think about how we're going to approximate g prime of 20, okay? So we have to figure out where 20 is on the independent variable line. We have to draw on a tangent line at 20, and then we have to use that tangent line to approximate the slope. So once we have the line, we want to think about what points are on that line and see if we can approximate the slope of that line. Okay, so that's going to be our plan here. I want you to try it out. I want you to take 2 minutes, think about how you would draw in the tangent line, what some points it may cross through, and then try to approximate the slope of that line to the best of your ability. At the very least, you should be able to identify if the slope of that line is going to be positive, negative, or 0 based on what it would look like. Okay, so take 2 minutes, try it out, see how it comes out for an approximation, and then we'll go through it together. Okay, take about 30 more seconds. Okay, so here if we look at the axes, we see the units of the dependent variable is going to be in kilograms, and the units of the independent variable is going to be in weeks. So we are trying to understand what's happening after 20 weeks, right? So what we need to do is we need to go to where 20 is, which is just about between 16 and 24, because we're counting by fours here. We go up to the function and we sketch in a tangent line. Now, your tangent line might not be exactly the same as mine, but again, it should be in the general vicinity of what I got, right? It doesn't have to be exact because we are approximating here. So we want to pick 2 points on this line to approximate the slope of the line, because we can approximate a slope doing change in y over change in x. So the points that I used are the points 40, 1.5. So that's where it looked like it crossed to me, right? So that's the 1.5, that's 40. And then I also used the point 16, 0, because that's what it looked like it crossed over here to me. But you can use any 2 points on this line, right? You could have used 32, 1. You could have used 20 and maybe, I don't know, 0.25, but any 2 points that look like they're on the line is what we want to use to approximate. So in order to approximate the slope here, we're going to do the change in y over the change in x, right? So when we think about the change in y, these numbers are pretty small. We have 1.5 minus 0 divided by 40 minus 16. So we can see that the numerator is going to be smaller than the denominator, so we're expecting a pretty small number. So I put this into my calculator because this was a decimal already, 1.5. So I put this whole thing in my calculator to crunch the number, and I got 0.0625. Okay, so that means that my approximation, 0.0625, is the rate at which my function is changing. And again, if your approximation is slightly different than mine, that's okay, but it should be, somewhere between, 0.04 and 0.08, right? That's the realm. And so in order to talk about what this number means, I need to really understand the units of this number. So again, I'm going to have the units of the dependent variable over the units of the independent variable. So kilograms per week. So if I want to talk about what this means, say at 20 weeks, because again, that is where we are evaluating this particular number. That's where we draw on our tangent line. The weight is changing by 0.0625 kilograms per week. So at that moment in time, we are expecting this baby to be gaining 0.0625 kilograms per week. That's the rate at which this weight is changing. Okay, so this had the added sort of layer of approximating the derivative by not only drawing in the tangent line, which we had sort of practiced doing before, just envisioning it, but actually then selecting points on that line to start to approximate the slope. Okay. So we're going to try another one just on units. And I'm not going to say a whole bunch about this other than I would really like you to make sure you are underlining the units, labeling them as the independent and dependent variable units, and then thinking about how we apply them to the 2 following statements. And so I'm just going to read it to you in case you can't see it, and then very briefly talk about the difference between these 2. So it says the time for a chemical reaction, capital T in minutes, is a function of the amount of catalyst present, A, in milliliters. So T equals F of A. Interpret the following. So you want to come up with a sentence to describe what's being said. So F of 100 equals 7. So this is not a derivative. This is just the function. So we want units for 100, we want units for 7, and then how do we talk about them together? And then part B is where we're talking about the rate of change or the derivative. So again, what are the units of 50? What are the units of 4? And how do we put them together? Okay, this one's a little bit harder than it looks. So please think about this carefully. I'm going to give you 2 minutes to try it out. And then we will go through it together. Okay, take about 30 more seconds. All right. So let's start by looking at the units that are given to us within the setup here. So we have capital T, time in minutes, and then lowercase a, which is catalyst in milliliters. So since we have T is a function of A, that means that the minutes are associated with the dependent variable, and the milliliters are associated with the independent variable. And this is a little tricky because time is more commonly associated with the independent variable, but in this case, it is not. So that's why we have to be really careful when we read through this problem. So let's start with f of 100 equals 7. So the 100, right, is the number that's being plugged into the function. And so the thing that's being plugged into the function is A. So that means we're talking about 100 milliliters. And that 7 is going to be our dependent variable. So we're talking about 7 minutes. Okay. So how do we put these two numbers together in the context of what's happening here? So we're talking about a chemical reaction. Okay. So we could say something like when 100 milliliters of catalyst are present, the reaction takes 7 minutes. Okay, so we know 7 has to go with minutes, and that's talking about, you know, the chemical reaction and how long it takes, and that the 100 has to go with the amount of catalyst in milliliters. So we need to put that all together to come up with a sentence that makes sense. This is obviously not the only way you can write the sentence. You could say something like, you know, the chemical reaction is 7 minutes when there is 100 milliliters of catalyst, right? But the idea is that the 100 milliliters of catalyst needs to be part of it, and that the reaction is 7 minutes is sort of the other piece. And then how you arrange the sentence doesn't really matter as long as those pieces are linked in the right ways. Okay, so that's how we interpret that first original statement. What happens now when we want to talk about the derivative? So as I mentioned before, and this is sort of one of the key points of what we're trying to really ingrain here, is that the number inside the variable is always related to the independent value. That doesn't change. What's changing is the unit of what's outside the equal sign. So the 50 is also talking about milliliters. Okay, so whatever is inside the function, right, the units of that don't change as you take derivatives. We're always talking about which moment in time. And so this is always going to have a single unit for the number that's inside. What's going to change is the output. Okay, so this 4. So when we think about this 4, okay, remember, we're going to do the dependent variable units over the independent variable units. So that means we have 4 minutes per milliliter. Now, that sounds a little awkward. So we really need to think about what that means in this context, right? So we know we're evaluating what happens when we have 50 milliliters of catalyst. Okay, that's sort of the when, that's the moment. So we can start our interpretation with when 50 milliliters of catalyst are present, because that's the moment. Now we need to figure out what this means. So remember, this is talking about the rate of change of the reaction. So when we talk about the reaction, we would say the reaction is increasing, and I'll talk about why we say increasing in a minute, by 4 minutes per milliliter, and we can add in the word added if we think that makes sense. So what this rate is telling me is that when I have 50 milliliters of catalyst present, that the reaction is speeding up by 4 minutes for every milliliter that I add. Okay, and so because this is positive, I know that the reaction is increasing. I could use the word changing if I wanted to be a little less specific, if I was a little bit worried about making sure to justify that. But in reality, what's happening is the reaction is increasing by 4 minutes per milliliter added. Okay, so like I said, this one's a little tricky because typically time is an independent variable, but it doesn't have to be. So that's why we need to be really careful about reading the initial problem and identifying what are the dependent units and what are the independent units. Okay. Well, let's look at another one. So just a couple of, tying it in practice types of things here. So the amount of medicine in mg, which is milligrams, found in the bloodstream, C of t, is a function of time t in minutes after taking the drug. So what does that mean? So let's say you have a headache and you take an Advil. If someone was measuring the amount of Advil in your blood, that's what we are measuring here. So it's the amount of whatever medicine it is in milligrams that's in your bloodstream after a certain amount of time of taking the drug. Okay, so for this one, I want you to interpret the statement C of 35 equals 90. So again, thinking about the units, thinking about what 35 and 90 mean and putting them together. I want you to write the derivative of this function using Leibniz notation. So that's when we had dy dx, but now I want you to think about what the variables are here and try to adjust that accordingly. And then for part C, it's another interpretation, but now of the derivative. So again, thinking about the 15 and the 7 and the units and how we would put them together. Okay, so take 2.5 minutes, see if you can work out these 3 pieces, and then we'll go through it together. Okay, take about 30 more seconds. All right. So again, we want to go through, figure out the units of the dependent variable and the units of the independent variable. Here we have milligrams, which are connected to C of t. So that is our dependent variable in units, milligrams here. And then over here, we have time t in minutes, which is going to be our independent variable units. Okay. So for part A, when we interpret the statement C of 35 equals 90, we're trying to think about what does the 35 mean and what does the 90 mean. So 35 is t, right? Because that's the number inside the function, and t is time in minutes. So when we talk about 35, we're talking about 35 minutes. And when we talk about 90, right? So the 90 is our dependent value here. And that's going to be in milligrams. So if we were going to put this together in a sentence, we would say something like, after 35 minutes, there are 90 milligrams of the drug in the blood. Something like that. Okay, where 35 minutes is the time that we are considering, and we're asking, well, how much of the drug is found in the blood, right? Well, 90 milligrams were found. Okay, so that's how we would put something like that together. For part B, when we're talking about Leibniz notation, we are trying to figure out what is the dependent variable, like what the actual variable we're using, and what is the independent variable we're using. So the notation, if we wanted to find the derivative for this problem, you would see it as dc dt, because c is the dependent variable and t is the independent. So this says take the derivative of c with respect to t. So that's how we would ask for the derivative if we were using Leibniz notation. And just so you can sort of see the map, the Newton notation would be c prime of t if we were looking for the derivative. Okay, so those are the notations we would use. And then for part C, we're interpreting the statement C prime of 15 equals 7. So again, when we talk about the 15, that is always going to be related to the independent variable because the thing you plug in is related to that. And so that's going to be minutes. And then the 7, this is where we have to use our derivative knowledge here. So again, we're going to take our dependent units, which are milligrams, over our independent, which are minutes. So if we want to put that all together, we would say something like, after 15 minutes, because that's the moment that we're evaluating, the amount of drug in the blood is, and again, you can use the word changing. I'm going to use increasing since this is positive. That means I know the direction of which I'm changing. So it's increasing by 7 milligrams per minute. So after 15 minutes, the amount of this drug is going up 7 milligrams every minute at 15 minutes. Now that rate might change. It's probably going to slow down. It's not going to go up forever by 7 milligrams per minute, but in that moment, that's how quickly it's changing. Okay. So again, when we are looking at problems, typically this is one piece of a bigger problem where we need to investigate what's happening and analyze it, but also understand the units and the context to help us understand how things are changing. Okay, so as I was saying before, we are going to be looking at this in terms of another application that's really important. And so the application we are going to consider here is called the tangent line approximation and local linearity. So these are actually the same thing, the tangent line approximation and local linearity, which is also sometimes called local linear approximation. And I want to talk about what this is before we talk about how we do it. Okay. So one of the main reasons that calculus is important for any major and sort of societally is because if we understand rates of change, we can use that to predict what we think will happen at a later point in time. And when you can predict how things are going to happen, that is helpful in so many ways, right? So we predict the weather using this type of work. We have a pretty good set of predictions around, you know, planet-related things, right? Rates of change, how quickly it's going around the sun. All of this stuff is related to calculus, right? The tides, we can figure out when and how the tides are coming in and out. Really, you know, when you do this with businesses, you can tell how the economy is going to do. All of this has to do with evaluating how quickly things are changing, which is calculus, and using some of these tools to make fairly well-established predictions. Now, are predictions 100% reliable? No, never, right? So something could change at any point of time that invalidates your prediction, but we are able to get a pretty reasonable guess at how things are going to work by using derivatives and calculus. And so this is sort of our first, I guess it's our second, because we did periodic functions to talk about this. But this is our first sort of calculus approach at making a prediction about information we don't have. And so the way that this type of prediction works, I'm going to draw a picture to sort of give you an idea, is that let's say we have a function and we have some data that goes to this point right here. Okay, this is our point in time. This is what we know up until this point, right? So what we're going to do is we're going to think about how quickly the function is changing at that point, right? So we have our tangent line. And so what we say is, hey, if we know how quickly we are changing at this point, we can then predict what's going to happen later by applying that rate of change to the actual point where we had information. So if we were going to guess what happened, say, at this point in time, right, the red point in time, we would kind of guess this, right? And so it's like wherever it is on the tangent line from that point forward. Now, the caveat of this is when we are really close to the actual point where we had information that we knew, this approximation technique is pretty good, right? But as we get further and further away from the point that we knew, the approximation gets worse and worse. So like if we were going to talk about what's happening at this point in time, like way over here, and we're guessing this, that's a pretty bad approximation because we are not close to the original point that we actually knew. So the further we are from our last known point, the worse our approximation is, right? Because we can see that this is going up and down. And so we expect that it'll keep going up and down. So the further away we go, the less accurate it's going to be. Okay, so what does this process look like that we come up with this line for approximating? It's called the tangent line approximation because we're using the tangent line. And again, we also call it local linearity. So what we can do is we can find the approximate value of a function at a point if we have information about a point near the point we are interested in. So this is the point where we actually had some information, and then we're trying to guess what's happening here. They're near each other. So we can use our information from what we know to try to approximate what we don't know. Okay, so the two things we need to be able to do this is we need information about a point, so the actual functional value, as well as information about the derivative. So how quickly are we changing? If we have information about the functional value and the derivative, then we can do this approximation. And the way it works is this is sort of the general formula. It says f of x is approximately f of a plus f prime of a times delta x. So what does this mean? So this and this are points we have. Okay, so you will be given the value of the function at a point and the value of the derivative at a point. Okay, f of x, this is a little confusing. This is the point we want. Okay, it's not a function. X is going to be a value. So let's say we're trying to figure out what's happening at f of 10. Right, this is the point we want. These are the points we have. And then delta x is going to be the difference between the points that we have and the point that we want. Okay, so let's see. I'll write this over here. So we're going to do x minus a. So the point that we want minus the point that we have. So how far away are we trying to approximate? Okay, that's sort of the goal here. So let's look at an example. We'll do one part of it together and one part of it you'll try on your own to see how we can apply this. So suppose that a particular function has g of 5 equals 10 and g prime of 5 equals 3. We want to use this information to approximate g of 7 and g of 1. So we'll do g of 7 together. So g of 7, that's the point we want. So that's going to be approximately. Now we go to the point we have. So notice that we have g of 5 and g prime of 5. That's the information we're given, and that's the point we have. So we know that g of 7, we can take the value of g of 5 and add to it g prime of 5, which is going to be the rate at which we were changing, times the difference between the point we want and the point that we have. So we're going to do 7 minus 2 here. Okay, so g of 5, we can plug in the value of 10. G prime of 5, we plug in the value of 3. 7 minus 2 is 5. Now we have to make sure we do our order of operations correctly here. We have to multiply these two numbers together before we add them over here. Okay, so here, where was I? Oh, go back for a moment. This should be a 5. I don't know why I wrote 2. So this is the point we have, 7, minus the point we are looking for. So we're looking for the difference between 7 and 5. I think I did the calculation in my head and wrote 2, and that was wrong. So 7 minus 5 is 2. So we are 2 units away from 5, right? That's how far we are moving. So that's what we have to multiply our rate by. So 10 plus 3 times 2 is going to be 16. Okay, so we know that we were at 5, right? G of 5. And when we were at g of 5, the value was 10. So that's our starting point. And then we were changing by 3 units. So here, if we move 2 units away, so from 5 to 7, we multiply the rate 2 times, which gives us 6, added on to our starting point, and that's how we end up with 16. Okay, now I want to point out here, this order is important. What do I mean by the order? So we're always going to do the number we want minus the value we have. And that's going to be important because sometimes that's going to result in a negative number, and that's what we want. Okay, so it's always the value we're looking for minus the value we have. So if this was 10, we would do 10 minus 5. If this was 1, like we'll see here, we would do 1 minus 5, right? So it's always this value minus this value. So that order is important. The other thing I want to point out is that here the order of operations is also important. You always want to make sure you do this multiplication first. The number one reason students get this wrong is because they do the addition first and then multiply. And so if you did 10 plus 3 is 13 times 2 is 26, that's a different value. You have to multiply these two numbers before you add the 10. Okay, so I want you to try g of 1. So you're going to set it up the same way, okay, with the information we have, which is g of 5 and g prime of 5. And then we're multiplying by the number we want minus the number we have, and then we'll crunch that number. Okay, so take, I don't know, a minute and a half, see if you can fill in those numbers to make sure we can get an accurate approximation, and then we will go through it together. Okay, take another 30 seconds. Okay, so again, the information we have hasn't changed. It's at what's happening at g of 5. But now we want to use it to try to figure out what was happening at g of 1. So for whatever reason, we don't have that information of what's happening at g of 1. So we do g of 5 plus g prime of 5. And now we need to figure out how far away we are approximating. So we take the number that we are looking for minus the number we have. So 1 minus 5. So again, that order is important, and you will see that that's going to result in something negative, which is what we need because we're sort of going backwards on the function from 5 to 1. So when we plug in the values, g of 5 is 10, g prime of 5 was 3. Now we do 1 minus 5, which is negative 4. And again, we want to make sure we crunch this number first. So 3 times negative 4 is negative 12, plus 10 is going to give me negative 2. So our approximation for g of 1 is going to be negative 2. Now, I do want to point out that g of 7 is a better approximation than g of 1 because 7 is closer to 5 than 1 is to 5. So again, the further away you move from the information you have, the worse your approximation is. So you want to try to stay as close as possible. So g of 7, probably fine. G of 1, a little bit worse. But if you were going to approximate g of 200, that's going to not be a very good approximation because you're really far away from the value you have. Okay, so let's look at this with another example as a word problem. So we know we want to use this particular process and method to approximate. So we need to think about how we can write the information we have in the word problem to be able to use this. So here, suppose the population of a town was recorded starting in the year 2000. In 2006, the population of the town was 125,000, and the town's population was increasing at a rate of 3,200 people per year. Use this information to approximate the size of the population in 2013. Okay, so I want you to think about what is the information we have, how can we write that using mathematical notation, and then what is the population we want, and how can we use this process to approximate it. So I'm going to give you 2 minutes, see what you can come up with, try to write it out, and see what you can come up with for a prediction for the population in 2013. Okay, take about 30 more seconds. Okay. So one of the things we really want to think about here is how we can write the information we have to organize it in a way that we can use. So notice that we know that the town started recording in the year 2000, but now we're talking about what's happening in 2006. So for me, I'm thinking we're talking about what's happening at t=6. You could certainly use time equals 2006, right? It's going to work out the same way, but I'm going to use t=6. So what do I know? I know that the population in 2006 is 125,000. So that's how I can organize that mathematically. I also know that the population rate of change in 2006, so still at 6, is 3,200 people per year. So I have information at a point and information about the derivative at a point, which is what I need to use this type of approach. So what am I actually looking for here? I'm looking for the population in 2013. So since I use 6, I'm going to use 13 here. If you use 2006, you would use 2013, right? So P of 13 is going to use P of 6 plus P prime of 6 times 13 minus 6. So that's the number of years I'm predicting away. So now I'm going to fill in all the numbers that I know. So P of 6 is 125,000 plus P prime of 6 is 3,200 times, now 13 minus 6 is 7. So I'm going to multiply the 3,200 by 7 first, which is going to give me 22,400. I run out of space, so I'm not going to write that, but you would multiply first and then add, and you get 147,400 as the size of the population. And so you may see sort of approximations of the world population for different points in time, or predictions for the size of the population in the US. This is what's sort of going on behind the scenes. We're taking the current population and considering the rate at which the population is changing in that year to then predict out what we think the population will be in future years, right? This is actually something that we do quite commonly when people are considering, world resources and things like that. So that's another way that we can see this tangent line approximation, where we have to take the information from the word problem and sort of get it into math form, and then we're able to use this process. One other way that this comes up is with data in a table, which is similar but different. So suppose that the table below gives the total sales in millions of CDs for a music store as a function of time in years. So what this is saying is that in 2008, there were 6.25 million CDs sold. So this is in millions, okay? We want to use the table above to approximate the sales in 2013 using this process. So notice that the information we have here only goes through 2012. So how can we use this information to predict what we think will happen in 2013? So again, we need to think about what is the most recent information we have that we can use to help make this prediction, okay? So think about what you know from before about tables. We do know how to find derivatives on tables. We've done that before. And so again, what we are trying to approximate is the total sales, F of t, in the year 2013. Okay, so this is what we want. So think about how we can use the information from the table to come up with the best approximation for the total sales. So I want you to take 2 minutes, see if you can figure out how to put this all together. And again, keep in mind that the further we are away from this year, the worse the approximation. So we want to stay as close to 2013 as we can. Okay, so take 2 minutes and then we'll go through it together. Okay, take about 30 more seconds. Okay, so given the information on the table, 2012 is the year that is closest to 2013. So ideally, we would use the information that we have from 2012 for our approximation. So the question is, do we have all the information we need from 2012? Well, we do know the functional value of 2012. We know how many CDs were sold then. So 4.5 million CDs. But the question is, what about the derivative? Well, we don't have the derivatives at any of the points, but we have learned how to approximate the derivative on a table. Since this is on an end, we would use the point next to it to approximate the derivative at 2012 by doing the change in y over the change in x. So we would do 4.25 minus 4.7 divided by 2012 minus 2011, and that would give us an approximation for the derivative. So here I have negative 0.45 is what you get when you subtract those and divide by 1. And then times 2013 minus 2012, which is 1 year away. So when you crunch those numbers, you get 4.05. Okay, and remember, these are going to be in millions of CDs. Okay, and so here, million CDs. So what's the process here? So we're going to get value and then approximate derivative. So if you have a table, you want to use the point closest to the point that you have, and then you can approximate as long as you have the skill of approximating the derivative, which we've learned before. The one thing I do want to point out, though, is that when you approximate a derivative within an already approximation, that sort of waters down how accurate it'll be. So we've talked about being close to be accurate, but also if you approximate within approximation, you also have a little more uncertainty on how close it'll be. But since we are using 2012 to talk about 2013, this is the closest sort of approximation we can use. So while this is going to be the most approximate in terms of being close to 2013, it's still an approximation within an approximation, which sort of waters down the whole thing. Okay, so keep that in mind. You know, if you're using this for predictability, you want to think about how reliable is it, and then overall, you know, if you're approximating within an approximation, you just have to be a little careful about the validity of it. We can do it, but how accurate it is not always as accurate as if we knew for sure what the derivative was, right? If it wasn't an approximation. Okay, so on Tuesday of next week, we're going to pick up with graphing. So, you know, you graphed in 2.2, we're going to be going to second derivatives and graphing there, and also doing some marginal analysis. So have a great weekend, and I will see you guys next week on Tuesday.